All right, in this video, we're going to take a look at falling objects and how the equations and our understanding of motion applies to falling objects. So let's first watch, this is a quick 3-minute clip from a popular Australian TV show about falling objects.
Let's say a Jack holds both balls above his head, and then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time.
I expect them to both land at the same time.
Same time. Same time.
Well,
I think they both will.
This one to hit the ground first. However, they would actually both hit the ground at the same time.
Yeah.
Why is that?
Science.
Yeah, science.
Now, the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed.
From this height, yeah, pretty much.
Just a constant speed all the way down.
Speed? Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar.
In terms of gravitational pull, they both are the same and they'll fall at the same rate. I'm not like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you've told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier. And has more gravitational pull.
All right, so in this video, the video you just saw, I wanted to tackle the one misconception, and we've already seen the video of the hammer and feather on the moon where there's no air. And we see that it in fact is air that keeps the feather from hitting the ground at the same time as the hammer when that experiment's done on Earth. However, when that experiment's done on the moon, we saw that they were the same rate. And so here, this TV show in Australia countered or asked regular people what the reason or what the difference was between the heavy black ball and the lighter basketball. And we saw some of the misconceptions. So let me give you a couple terms here to kind of use to put in our toolbox. The first term is free fall. So an object is considered to be in free fall when the only force acting on it is the gravitational force of the Earth. So something falling from the sky, a baseball hit in the air, a rock falling down the side of a mountain into the Grand Canyon. These are all things that are in free fall. And when an object's in free fall, the acceleration on it for the object in free fall acceleration is 9.8 meters per second squared. Okay, so if we have a cliff here and I throw a ball off the cliff, right? Here's my baseball. Okay, initially it has a speed of 0 meters per second. 1 second later, its speed will be 9.8 meters per second. 1 second later, so after the ball has been falling for 2 seconds, the speed of the ball will be 19.6 meters per second. And you can see after 3 seconds, right, the speed of the ball will be 29.4 meters per second. So we're just adding 9.8 meters per second per second. So a couple things that are useful for us in physics. One of these is called a motion map. Okay, and a motion map shows the motion of an object. And the way this would work for the baseball, now I've drawn the baseballs here equally spaced out. But this isn't actually how they would fall, right? We know a falling object, if its speed is increasing, the distance it will fall each second is greater and greater and greater. And I'll show you that in a second. So the motion map for a falling baseball would look like this. Something like this, where each ball represents 1 second, and we can see that the gap in between is the displacement. So a falling object, the distance it falls increases, and I'll show you this here now. Let's look at this. All right, so in the video here, we're going to see drops of water falling from a hose, and they've been a dye has been added, a green dye called fluorescein that helps them glow in the strobe light. And so essentially what you'll see here is each drop represents 1 second of time, because they have a strobe light kind of capturing each second in time. So like here to here is 1 second, from here to here is 1 second, from here to here is 1 second, and so on. So you can think of this as a time lapse of one drop. And what I want you to notice is as it falls, each second, the distance it falls each second is greater and greater and greater. And again, that's because the drops of water are under the free fall acceleration of 9.8 meters per second squared. So when we're dealing with free fall acceleration, free fall situations, all of the equations we had in the last couple videos still apply. Let's look at a sample problem. Actually, you know what? In the next video, we'll look at a sample problem. So for now, I'm just going to stop this video, and I'll put a practice problem video up. So that's it. Remember, physics is fun.